This is another video in the series Graph, Homomorphisms and Universal Algebra. Today will be more graph theoretic. I will present the theorem of Hell and Nesetril about finite undirected graphs. In fact, we'll prove a stronger theorem, which is based on a proof due to Bulatov. Let H be a finite undirected graph. The main result of today is that either H has a self-loop, or is bipartite, that is two-colorable, or it can primitively positively construct a triangle. Recall, this means that H can interpret primitively positively a graph which is homomorphically equivalent to K3. If a graph contains a loop, then its CSP is trivial because every graph homomorphically maps to a loop. If H is bipartite, then the CSP of H is polynomial time solvable too, because a graph homomorphically maps to a bipartite graph if and only if it is itself bipartite, and this can be checked in polynomial time. On the other hand, if a graph PP constructs a triangle, then its CSP is NP-hard, as we have seen earlier in the course. So today's theorem implies a complexity dichotomy. The CSP for H is in P or NP-complete. This was first proved by Hell and Nesetril. The proof that we will see today is based on a proof of Bulatov. However, we even take a little shortcut. I will comment on the difference later. Suppose that H is a finite undirected graph without loops, which is not bipartite. Our goal is to PP construct a triangle. We may assume that H does not PP construct a finite undirected graph which is not bipartite, loopless, and has fewer vertices. Because otherwise, if K3 has a PP construction in the small graph, it also has one in the original graph H, because PP constructibility is transitive. So we may then replace H by this small graph. Note that this implies in particular that H is a core, because the core of H must be loopless and cannot be bipartite. So if H would not be a core, then the core of H has fewer vertices than H and has a PP construction in H, and this is in contradiction to our assumption. Since our graph H is not bipartite, it must contain an odd cycle. Let K be the length of the shortest odd cycle. Then we consider the graph on the same vertex set whose edge z is e to the k minus 2. In this new undirected graph, two vertices are adjacent if they are linked by a path with k minus 2 edges. Observe that the new graph must contain a triangle. On the right, I draw an example where H is the 5 cycle. So here we would look at e to the 3, which is the edge relation of the 5 clique. So it contains a triangle. In general, since k was chosen to be minimal, the new graph is again loopless. Moreover, the edge relation of the new graph is primitively positively definable in the old graph. It follows that we may assume without loss of generality that H contains a triangle. The reason is that if K3 can be PP constructed from the new graph, then K3 can also be PP constructed from the old graph. So we may simply replace H by the new graph. We now prove a series of consequences of our two assumptions. The first consequence is that every vertex of H must be contained in a triangle. For this, we consider the primitive positive formula which says vertex X is contained in a triangle. Let S be the set of all vertices that satisfy this formula in H. I have a small example on the right. Since H contains a triangle, S will be non-empty, and the subgraph of H on S still contains a triangle. Moreover, the subgraph is also loopless and has a primitive positive interpretation in H. So our assumption implies that S must be the set of all vertices of H, and this proves the claim. Our second claim is that H does not contain a copy of K4. For this we prove a general lemma about core structures and primitive positive interpretations that is of independent interest. Suppose that B is a core structure and little c is an element of the domain of B. Then the expansion of B by the unary singleton relation capital C that just contains this element C is PP constructible in B. In order to prove this, we have to show that this expansion is homomorphically equivalent to a structure A with a primitive positive interpretation in B. Our primitive positive interpretation will be two-dimensional. Let O be the smallest subset of B that contains C and has a primitive positive definition phi in B. The domain formula delta of x, y of our two-dimensional interpretation is phi imposed on y. If R is a relation symbol of arity k from the signature of B, then the interpreting formula for R has arity to k and is the conjunction of R imposed on x1 up to xk and y1 equals y2 equals and so on equals yk and phi imposed on y1. Finally, the interpreting formula for the relation symbol capital C is the formula x equals y and phi imposed on x. Let A be the structure interpreted in B in this way. I claim that A and the expansion of B by the singleton relation capital C are homomorphically equivalent. The homomorphism from the expansion to A is given by A maps to A, C. And this is easy to see. If A1 up to AK is in the relation R, then A1, C and so on up to AK, C is in the respective relation of A. The relation capital C is also preserved because the pair C, C is in the relation for capital C in A. To define a homomorphism H back from A to the expansion, we pick for each element A in O an automorphism alpha sub A of B that maps A to C. Note that such an automorphism exists by the choice of O and the assumption that B is a core. This is a little exercise. Now, define H of A, B to be alpha sub B applied to A. It is straightforward to verify that this is indeed a homomorphism, and we invite the reader to press pause and verify it, or look it up in the script. It is pretty clear that our new lemma implies claim 2. Suppose for contradiction that H contains a copy of K4 as a subgraph. We already know that H is a core. To apply the lemma, we pick a vertex C from the copy of K4. The lemma then implies that the expansion of H by the singleton relation that just contains C is primitively positively constructible in H. Now consider the subgraph H' of H on all the vertices that are adjacent to C. H' is a proper subgraph of H because it does not contain C itself. It contains the other vertices of the copy of K4, so it must contain a triangle. Moreover, H' is primitively positively constructible in H, and this is in contradiction to our first assumption. And this proves the claim. We have seen now quite a number of tricks to reduce the problem and to primitively positively construct a triangle. Let's try this out on an example. what are these tricks? Taking cores, adding constants to cores, restricting to definable subsets, taking the k minus 2th power of the edge relation. I bet with these tricks you can classify almost all the finite undirected graphs you can come up with. But of course we want a general proof, a proof that works in general. And for this purpose, there's a very nice trick. The idea is that instead of interpreting a k3 primitively positively, we may also interpret a finite power of k3. This might be easier somehow, magically. But it suffices, because clearly a k3 and a finite power of k3 are homomorphically equivalent. So overall we'll get a primitive positive construction. And that's fine, that's what we want. For the next consequence of our assumptions, we need the concept of a diamond. This is simply the foreclique where we have removed an edge. We claim that our graph H must be diamond-free. That is, it does not contain a copy of a diamond as a subgraph. To prove this, let R be the binary relation defined by the following primitive positive formula. We obtain the formula from the canonical query of the diamond by existentially quantifying over the vertices of degree 3 and keeping the other two vertices, x and y, of the diamond as free variables. Let T be the transitive closure of this relation R. Observe that T is symmetric, because R is symmetric, clearly, and that T is reflexive. To see this, note that R is reflexive because every vertex is contained in a triangle, as we have already seen. Moreover, the relation T is primitively positively definable in H. We already know that R is primitively positively definable. And it is clear that R squared, R to the third, and so on are also primitively positively definable. However, in general, the transitive closure of a relation is not primitively positively definable, since we have no bound on the exponent. But since we are in a finite structure, the transitive closure can be computed by taking a finite power, and hence is primitively positively definable. The natural reaction, if we see an equivalence relation that is primitively positively definable, is to factor by this equivalence relation. We consider the graph whose vertices are the equivalence classes of T and which has an edge between two equivalence classes if there is an edge between some of the vertices of these two classes. We denote the resulting graph by H/T. Note that H/T is primitively positively interpretable in H because T is primitively positively definable in H. We claim that H/T does not contain loops. For this, it suffices to prove that the intersection of T and E is empty. Suppose for contradiction that the intersection contains an edge AB. Choose AB in such a way that the length n of the shortest sequence of diamonds leading from A to B is smallest possible. Note that n must be at least 2, because otherwise there would be a k4, which is impossible, as we have seen earlier. Let me stress again that from all pairs AB in the intersection of T and E, we choose the pair such that n is smallest possible. Suppose first that n is even, of the form 2k. Let u1, v1, uk plus 1 and vk plus 1 be as in the picture that I've drawn for you. Let S be the set defined by the following primitive positive formula. We can imagine this formula as walking along the diamonds. We start from uk plus 1 and vk plus 1. Then the variable x1 could therefore be ak or ak plus 1. Then we follow k minus 1 diamonds, and at the end we follow another edge. The set of all vertices that you can reach like this is S. From looking at the picture, it becomes clear that U1 and V1 are both in S by following the diamonds to the left. On the other hand, A0 is also in S by following the diamonds to the right and traversing the edge that I have drawn in blue at the end. So we see that S contains a triangle, namely the triangle A0, U1, V1. Also note that AN is not in S by the minimal choice of n. So we found the primitive positive interpretation of a smaller graph which contains a triangle and no loops, in contradiction to our assumption. In the case that n is odd, one can derive similarly a contradiction. So we conclude that the vector graph H/T does not contain loops. Also note that the vector graph contains a triangle, because H contains a triangle. And if ABC is a triangle in H, then the classes of A, B, and C form a triangle in the vector graph. These classes are distinct because H/T does not contain loops. Our assumption therefore implies that all classes of T must have size 1. And this in turn implies that H is diamond-free and concludes the proof of claim 3. We are now almost done with the proof. We know that our finite undirected graph H contains a triangle, contains no loops, does not contain a K4, and does not even contain a diamond. What's so good about being diamond-free? Our goal is to interpret primitively positively a K3. And remember our idea, to interpret primitively positively a finite power of K3 instead. Finite powers of K3 are diamond-free. In the script, you will find the proof of the following proposition. If we have a homomorphism from a finite power of K3 into a diamond-free graph, then the image of the homomorphism is isomorphic to a finite power of K3. The proof of this lemma is somewhat technical and doesn't fit into the video. But let's instead see how to finish the proof using this lemma. We construct a strictly increasing sequence, G1, G2, and so on, of subgraphs of H, such that Gi induces in H a copy of some finite power of K3. We start our construction with any triangle in H. Suppose now that Gi has already been constructed and that we want to construct Gi plus 1. In our construction we distinguish two cases. The first is that Gi is primitively positively definable in H, possibly using constants. In this case, we are done, as we will see later. Otherwise, if there is no such definition, then by a theorem that we have seen earlier in this course, we know that there exists a polymorphism f of H that does not preserve Gi. So there are elements u1 up to uk in Gi, where k is the arity of f, such that f applied to u1 up to uk is not in Gi. In this case, we define Gi plus 1 to be the image of the restriction of f to Gi to the k. This restriction is a homomorphism from a finite direct power of K3 into the diamond-free graph H. So by the proposition, Gi plus 1 induces a copy of a finite power of K3. Since F is idempotent, Gi is a subset of Gi plus 1. It is even a strict subset, because F applied to U1 up to UK is not in Gi. So we obtain a strictly increasing sequence. But since H is a finite graph, we cannot keep on increasing forever. We therefore must eventually run into the first case. So there exists some M, such that Gm has a primitive positive definition in H with constants. Since K3 is homomorphically equivalent to the subgraph induced by Gm, we found a primitive positive construction of K3 in H. Finally, this concludes the proof. The theorem of Bulatov, Hell and Nesetril is not just any complexity dichotomy in theoretical computer science. As you can see in the video about Zigger's theorem, it implies a fundamental dichotomy for all finite algebras, and in fact for all finite structures. It describes a very important boundary in discrete mathematics.